A note on our Canvas page. We have the module with the syllabus, some reference files, a handout. That's the example I did from last week. Bunch of web links. And way down here under the web links is where the keys to the homework show up. So if you've got questions about the homework, take a look at that, then come talk to me. Otherwise, you should have the next section, chapter 1, section 2 for me. I will collect that now, and then we'll move on from there. I know what I'm doing this weekend. Okay. With our propositional variables and our structures of propositions, I want to add a short diversion into grammar. Wait a minute, this isn't an English class. Same idea though. The basic two parts of a sentence. What are the basic two parts of a sentence? Everybody remember the grammar and proposition class? Subject, predicate. The subject is the thing doing, the predicate is what they do. I am old. ABC used to run Schoolhouse Rock. Do you remember Schoolhouse? Have you ever heard of Schoolhouse Rock? There's a Schoolhouse Rock on subjects and predicates. Go look up Mr. Morton, like the salt company, and you'll find that one. So if I think about a mathematical sentence, now this is not a proposition, because I don't know if it's true or false, because I don't know what X is. But I have a subject and a predicate. Yes? I have a subject, whatever this number is, and then I have a predicate. And now I can make a predicate function. This is a function of X. So now, when you evaluate this by putting in different values of X, you can decide on a truth value. You should be able to tell me which of these are true, which of these are false, and assign a truth value to each of those three now statements, actual propositions, because we have specific values for X. So, is P of 2 true or false? That's true. P of 6. P of 5, because that's a strictly less than. So I have truth values for a propositional function based on the value assigned to the propositional variable. Oh, okay. I don't have to have one variable functions. That's a two variable propositional function. And now I would have to give values for both X and Y for me to know whether the result is true or false. I can have as many variables as I want. An n variable propositional function, or wait a minute, We talked about our operators, right? We had unary and binary and so forth, right? When our operators, it was a binary operation that worked on two propositions. I can think of this as an n-ary function or an n-ary predicate. I prefer using the phrase propositional function over predicate, but that's just a personal peccadillo of mine, and that's okay. The truth value of a predicate function allows me to decide which piece to use in a program in an if-then-else statement, right? If X is bigger than 0, then do this. Otherwise, well, if it's true, I do this one. If it's false, I do this one. Just tell me what X is. You can't evaluate it until we know a value. Have you gone over debuggers in your class, step through debugging? A little? Short piece of badly written code. Trust me, badly written. I am not a coder. It's kind of C-ish. And most of the code I'm going to write is going to look sort of like it's designed, but it's going to be a lot more English than it is proper symbols. So this is usually referred to as pseudocode and is commonly used in algorithm design at the high level before you actually start engaging whatever language you're going to use it in. Because I can write this and then I can translate this into Rails or C or Python or whatever language the app needs to run on based on the hardware. I start with a known value for X. And then I run into this predicate function, which tells me which branch of the decision to make. And then I have a new value for X, right? X is assigned a value. Right now, before I've done anything, what's the value of X? Right there. That's the precondition. I run the program, I have a post condition. What's the value of X? Because it only goes down if I start with something negative. That's not negative, it's going to go up. There we go. Pre and post conditions are how we do step through debugging. Okay, run this line of code. What happened to all of my variables? In a lot of algorithmic tracing, what we're going to do is we're going to look at an algorithm. We're going to write out all the variables. Okay, I did this line. What changed? I did this loop. What changed? What's the precondition? Execute. What's the post condition? Runaway loops are because I don't have a good stop point to my looping condition, so I can catch that without actually running the code. There's an example on page 43, example 7 in the text as well. Talk about pre and post conditions. Questions? Page 43. Okay. So now I understand what a predicate is and what a predicate function kind of does. What's the other title word in this section? All right, quantifier. What's the root of the word quantifier? Which means count. How many? Quant. So I want to try and write in logic quantifiers that allow me to avoid assigning specific values to my propositional variables and still have decidable results for my propositional functions. So instead of actually saying, for this x, it does this value, for this x, it does this value, for this x, it does this value, I want to try and write a sentence that sort of groups this and really gives me a better way of hanging on to multiple values at the same time. In formal logic, we really only devolve to two different ones. So I'm just going to look at those two. There's a little bit of a variation in there occasionally. We'll talk about that. Let's try again. The universal quantifier is written as an upside down capital A. So I could say something like this: for all x, P of x. Aha. Okay, it applies to every value of x available in our universe. Aha, universal makes sense now. I get that. P of x is true for every possible x in the universe I am talking about. What does that sentence say in English? Seth? Ah, when you add one to a number, it got bigger. Do you agree that this sentence is true? I have a problem. What kinds of numbers am I using? I didn't say that. We all made the assumption that I'm using the numbers you all are used to, right? So when I add one, stuff gets bigger. That makes sense. But then literally, I didn't specify that. Somehow I should specify what kind of numbers I'm using, because there are lots of different sets of numbers out there. I'm going to go back to my algebra class. What happens when you take the square root of -1? Your calculator goes, but I get a complex number. So if instead of working in the real numbers, I was working in complex numbers, this sentence would actually be false. Because the idea of greater than in the complex numbers is a problem, because complex numbers are two-dimensional. They have that real part, and then they have that I part on them, and damn it, length works differently there. So I have to specify the universe I'm working in. So if I say, when I'm using x is an element of the real numbers. We'll talk more about sets in another couple of weeks, but I'm basically saying, okay, only use real numbers. Yes, this is true. But I need to specify that. Now I could specify that back here. And I could say, hey, for all x's in the real numbers, this property is true. So you notice where I put the specification of my domain, my universe. This is an important programming idea. What happens when you pass a Boolean to an integer function? It goes, I don't know what the hell to do with this. So you need to tell it, oh, you're only allowed to accept strings. You're only allowed to accept integers. You're only allowed to accept doubles or quadruples, whatever precision is necessary for your algorithm. You're only allowed to accept integers. But if you don't specify, your code's not going to compile. Questions?
What did you say again? All values in a second.
For all x in the real numbers. So that little funky looking E means in. And this crazy looking R is the real numbers. That extra vertical line is to try and denote a bold written with the side of the piece of chalk on the chalkboard. I don't have chalk.
So in the second part, you made it true because you went to you declared that for all values of X in real numbers.
Bingo. So I put the definition there. Without that piece, I don't know if this is true or false, but with that piece, there's no question it's true. But again, I don't know what language you're writing in. I hate to admit this, but my first programming language was BASIC. And my college programming language was Pascal, which is C++'s great-great-grandfather. I'm old as far as computers are concerned. So I don't know what this looks like when you write a called function in C. I've never written in C. I don't know what this looks like in Python. I've never written in Python. I've literally watched no modern coding. The amount of coding I needed to do for my PhD thesis, I outsourced. My friend Robin deconstructed all the code I needed. Man, was he good. So I don't even do that. But that's why I'm telling you, from a computer science standpoint, this is an integral part of your design of your called subroutine. It's in there automatically. I want to think like that. So I want to make it part of my logical pieces as well. It turns out this particular sentence, as I said, works in the real numbers, but the real numbers is an infinite collection. When I have a finite collection, maybe this is the wrong sentence for a finite collection, but if I have a finite collection, our universe of discourse, the set of crap we're talking about, if our universe of discourse is finite, then you could actually go through them one at a time and check. And that makes a universal statement an and statement. Because I want it to be true for all of them. So it's got to be true for the first one, and the second one, and the third one, and until I get to the last one. But that only works if I have a finite number of things. Let me give you an example of a finite collection. The funky looking Z means I'm dealing with a set of numbers, but Z is from the German word Zahlen, means integers. So that's what the Z means, integer. But the subscript 3 means I'm going to divide by 3 and take the remainders. I'm going to go modulo 3. The mod command, I see, okay. We're going to call this the modulus. Okay, if you pick any whole number, any integer, you divide it by 3, what are the possible remainders? 0, 1, and 2, that's it. So this set consists only of the numbers 0, 1, and 2. Now here's the fun part. I can add in this set of numbers. I can multiply in this set of numbers, as long as I do the adding and then divide by 3 and take the remainder. I do the multiplying, divide by 3 and take the remainder. So, here's a statement. Okay, I did something weird. For all x in my set, take away 0. When you square the number, you get 1. That's weird, isn't it? But I can really check that by checking the only 2 options that are allowed here. The only 2 possible x's are either x is 1 or x is 2. Those are the only ones that I need to worry about, yes? So what's 1 times 1? Divide by 3, take the remainder. There are no 3's with 1 left over. That's equal to 1. What's 2 times 2? There is no 4, but I said 2 times 2 is 4. Divide by 3, what's the remainder? It's 1 3 with 1 left over. Quotient and remainder. That's how it divide, right? I have 1 3 with 1 left over. Yeah, 2 squared is equal to 1. There's a sentence you never thought you'd hear me utter in my entire life, right? It's a math class, man. 2 times 2 is not 1. It is in this universe. At the moment, in biology, I'm going to work in the set of human beings. I'm going to define the propositional function, T of x. X has 2 biological parents. Question. Is that sentence true or false? Yeah. I said X is a human being right up there. I defined it in advance, so I didn't need to define it in a sentence. I already said I'm working in the universe of human beings. Do you know somebody who only has 1 parent? Biologically. We haven't cloned anybody yet, so I'm pretty sure that's true. That everybody has to come from 1 sperm cell and 1 egg cell at the moment. Whether that's fertilized in the body or outside, artificial insemination works. In vitro fertilization works. We know how these things work. We have yet to find a human being whose genetic material only comes from 1 person. But
I was just gonna ask, are we only looking at what has happened or what is possible?
what has happened right now in the world, is this sentence true or false? Right now, this sentence is true. But Steve Bassett, who was on biology faculty here, retired a couple years ago, has a huge interest in mitochondrial diseases. And they are studying how to take mitochondria out of a healthy cell and replace diseased mitochondrial tissue in someone else. And they're trying to do it in utero. They're trying to do it in the egg cell before that egg is fertilized, in the sperm cell before that sperm is fertilized. Well, if you take the cell that's got the mitochondrial piece out of the cell, you have to put another mitochondria in there. If that comes from a 3rd person, you'll have somebody with 3 genetic parents. If we ever get cloning right, you could have somebody with 1 genetic parent. If I made X the universe of sheep, then we've already cloned a sheep, then the sentence would be false. Because we've cloned a sheep. Remember that. We've cloned 1 sheep. If I find 1 counterexample, the universally quantified sentence. Here's a way where I can really say it takes 1 bad apple to spoil the whole bunch. If I have 1 place where this giant and is false, then the whole thing is false. Questions?
Does that make it really hard to have a true statement in there because there's so many things that could be false?
That's a really, the difficult question is, how do I show that this universally quantified statement is true? And I'm not there yet. But that's one of the problems, you know, I mean, in computer science and math, in science in general, how do you know something's true? I'm asking a really deep philosophical question. What is truth anyway? We'll have a discussion about that. Just not today. Other questions? Okay. Especially in the cases where I have not finite infinite sets of things like the real numbers or all the integers, showing the universally quantified statement is true is not obvious. But we've done them in math. Here's one that you should have done in your algebra class. Long time ago in a galaxy far, far away. We did polynomial inequalities in our algebra class. Anybody remember doing this crap? No, it's gone. I pooped it out of my head years ago because I haven't used it. Let's think about this for a moment. What does this sentence say? Dan?
Say all values of x, where x squared is greater than x.
That comma is the end of the hypothesis. So this is part of my domain of definition. So for all x, we're looking at reals, this x squared is bigger than, not if x squared is bigger than, there's no if then. I claim that if you take any number and you square it, it gets bigger. True or false?
False.
Why?
It's right.
Aha! What's 1/2 squared? 1/4, which is smaller. But if I'm looking at integers, then this is actually true. Because the only numbers where it's false are between 0 and 1. Before you look at me like I'm out of my mind, let's think about this sentence is the same as this one, right? Okay, wait a minute. Who's got a graphing calculator or a graphing device? If you've got your computer open, use the grapher on that. If you've got your phone, go to GeoGebra or Wolfram Alpha or whatever. I want you to graph y equals x squared minus x. When I graph that sucker, I get this picture. I'm going to blow this up, zoom in, and we see the only place where this is negative is between 0 and 1. So if I'm not allowed to use any fractions, it's never negative. So my universe of discourse, my choice of domain, functions have domains. My choice of domain matters. And that's what we specified here. So this one's false, but this one's true. So the same sentence can either be true or false depending on what set we are talking. Yes, sir.
So anything before the comma is if.
It's part of the quantifier. For all x. Comma, claim, we claim that. Maybe we should read the comma like that. For all x, we think that x squared is bigger than or equal to x.
And we immediately follows.
Well, that's my recommendation about the domain, right? Oh, what kind of x's are we talking about? We're talking about real numbers. I could also have written this sentence. For all x in R, x squared bigger than or equal to x. For all x in Z, x squared bigger than or equal to x, right? So I can either put the domain with the quantifier, or I have to specify it somewhere else. Normally in your coding functions, you specify it with the output variable, right? And then you specify what inputs are allowed, so each one has what type it is. So program subroutine name, y, integer, x, real, z double, whatever it is, right? You specify each one with it. I'm out of date in my code, I apologize. Ask Mr. Barry about that because I don't remember how variable specification goes in the modern languages. More questions? I think I'll try and do it this way more often so that it's easier to put those two pieces together. This is one quantifier, the universal. There's another one, the existential quantifier. All right, if universal meant all of them and I used an A, existential, I'll use an E. I need to make it look backwards so that it's clearly not the same symbol as just an E. Because E of X would look like a function. I want to be this, backwards E. That backwards E means there is, there exists, we can find. Those are all legitimate translations of this symbol. So if I were to write whoops. I forgot to write it down, Dan, I apologize, there it is. For all x in the real numbers, oh, sorry, not for all, there exists an x in the real numbers. So that x squared is equal to x. True or false? True? How do you know? 1 squared is 1. Love it. Is that the only one?
0 also equals 2.
0 squared is 0. I just said we could find one. I didn't say there was only one. There's one or more. There exists an x that does this. Some x. I don't know how many. But there's at least one out there. Again, it's going to depend on my domain, my universe of discourse. If my universe is finite, this is a giant or statement. Because I only need it to be true once. And if it's true once, this giant or statement is going to be true. problem. And this is why I usually use there exists rather than we can find. If I say there exists an X with this set of properties in whatever universe I'm working in, I might not know what that is. I might not know what the number is, but I know it exists. Again, you've done this in Calc 1. I hope, but I'm not sure if this semester's Calc 1 has gotten to continuity yet. You talk about continuity in Calc 1 this semester? Continuous? Who's in Calc 1 this term? Haven't gotten it? So that'll be next week. Continuous means you can make the picture without lifting your pencil. So once you graph something, you don't lift your pencil. One of the nice consequences is that means you know you go in between all the things. I claim, again, it's a real number. I apologize, I didn't write that down. Dang it, I got to get better at this. In R. There is some real number where this equation is 0. How the hell do I know that? Turns out, if you put in 0 to this left-hand side, what do you get when you plug in X equals 0? -1. What happens when you plug in 2? Because 2 cubed is 8. 8 minus 2 minus 1. Okay, wait a minute. If X equals 0, X cubed minus X minus 1 is -1. If X equals 2, X cubed minus X minus 1 is equal to 5. This function is continuous. It started out negative. As I went from left to right, it became positive. What has to happen somewhere in the middle? It's got to be 0. Otherwise, there would be some sort of light speed jump from one side of the x-axis to the other, right? We go from negative numbers to positive numbers, and we jump over the middle. I just said continuous meant that you hit everything in between. We'll talk about the more precise why. This is the intermediate value theorem, chapter 2, section 5-ish in the calculus. I don't know what the number is. I know it's between 0 and 2, but I don't know anything else. I just know it exists. It might be a fraction. It might be an irrational number. I don't know, but I know it's a real number because we're in the universe of real numbers. You sneakies. Again, that's why when I say we can find, I'm really saying somebody could find. There is such a number, I just don't know what it is yet. Questions? This is an example of a non-constructive solution. I know the solution exists, but I haven't actually found it. This is where I said there would be a variation. Some of these have variations on them. There's a version of the existential quantifier that puts a bang after it. Sorry, that's the Unix definition of the exclamation point. The bang symbol. This is a new twist. That exclamation point means unique. So if you see an existential quantifier and it's got that exclamation point on it, then it's changed our OR statement to an exclusive or. This can be true once and only once. Now, it's possible to write any sentence that you would write with this without it. It just gets more complicated. It's like writing the if and only if as two separate if-thens. We'll talk about that in our next class, but I just wanted you to see this version because it's in there. It's in our textbook. Please note, I've added these things to our logical universe, right? They're going to be parts of our sentences. I need to put them in order of operation. They should apply over all the others. So if I were to write something like this, if I want to give the existential quantifier a higher priority, this really means that I do it before the and. Same thing with the universal. Quantifiers have higher priority than our other logical operations at the moment. If we want it to go the other way, I'd need to put parentheses around the PN cubed. But that tells me the scope of my quantifier. What things does my quantifier apply to in the rest of the sentence? In this case, the quantifier only applies to the immediately connected propositional function. Yes, sir. Depends on which side the negation is on. I do negations first, right? So if the negation was here, then I would do the negation first and then this, right? There exists some x where not p of x. This thing is false somewhere. Right? So, for example, I could write this. I don't know what universe I'm working in. I don't know what these letters mean. I don't know what the propositional functions are. But let me see if I can translate what this says. There exists an x so that p of x and q of x. Right? And that's in parentheses. So both of those things should be true for that part to work. Or for every x, this property R of x.
Regular R, right?
Yep.
We're not trying to do a
No, that's just P, Q, R. It was the next letter in my line. Yeah, not real number of x. That's something else. So here, this x, this first x, and this second x, technically are different things, right? In that first part, I'm saying you can find some number somewhere, or some person, or some book. I don't know what the universe is. You can find something where both of these are true. Or for everything in the universe, this thing. Again, it's going to depend on what the universal discourse is. Either both these conditions are met once, or this condition is met all the time. This x is bound by this quantifier. This x is bound by this quantifier. If I had multiple letters involved, You're telling me you can find an X to make this work. For what Y? Any of them. But I only have to find it working once for this to be true. On the other hand, what changes now? Come on. Y is not bound here, right? There's no Y appearing in the quantifiers. So it could be all the X's, but it could be just for one Y. It could be for a handful of Y's. It could be for all the Y's, but I don't know. I only care about making sure it's true for all the X's. And maybe for each X, I find a different Y that works. I don't know. That's okay. I'm only saying you can find this for all the X's. Questions? Ian, you asked me about negations. One of the interesting things is where we put our negations and what they mean. So if I write this, that means for every X in the universe, the statement P of X is not true. For this to be true. If I write this, it means there's some X where the statement P of X is not true. Right? Question. The hell does that mean? It is not the case that for every X, P of X is true. That's the most awkward piece of English I've said today. I said some weird shit earlier this morning.
There is at least one instance in which it is false.
You De Morganed on me. Think about this. The universal quantifier we said was a giant and, right? If you have a negation outside an and, you switch them to ors, and we said that the existential was a giant or. So this sentence means the same thing as there is some X where it's false. It's not always true. I mean, somewhere it's false. On the other hand, it is not the case that it is not the case that there is some X where P of X is true. That's the negation on the outside of the or. That should become an and. These are just De Morgan's laws. If I say the sentence, every student in this class, a universe of discourses, this class, has had me as a teacher before this semester. What's the opposite of that? What's the negation of that sentence? At least one student has not had me as a teacher before this semester. And you know who you are. It is absolutely important to read these translations back into English carefully. My favorite, absolute favorite writer of logic did these wholeheartedly. Lewis Carroll has hundreds of these quantifier reversals in Alice in Wonderland and in Through the Looking Glass. You'll do one of them in the homework. I will see you all on Monday. Have a wonderful weekend. If you came in late and I still have your homework from before, or you have homework for me, please come give it to me. I will see you all on Monday.